How is it the only planet in the entire solar system to have life? The questions are endless, but we might have a few answers. Hey guys, welcome back to our channel. Today we're giving you a quick rundown on the history of the Earth. There are about 4.54 billion years worth of stuff to go through, so sit tight and keep on watching. It's hard to imagine a world that is nothing like the planet we are currently living on, but it's true. Back then, there were no beautiful oceans, mountains, trees, or even humans. It was just a planet that was absolutely uninhabitable. So let's talk about how Earth really came to be the place we call home. For all of it to make sense, we need to take a journey to the past, and we mean billions of years ago. The gravitational collapse of a small portion of a massive molecular cloud marked the beginning of the solar system's formation roughly 4.6 billion years ago. The Sun, a giant ball of hot plasma, was produced from the majority of the collapsing material, which also flattened a protoplanetary disk from which the other planets, different moons, asteroids, and other minor solar system components emerged. Planets such as Jupiter, Neptune, Uranus, and Saturn formed faster than the others, such as Earth, Mars, and Venus, and they were what we call gas giants, whereas the rest tend to be terrestrial planets. Still slowly circling the Sun, residual gases were responsible for the streams and waves in space. The enormous Jupiter became entangled in these currents and began to turn inwards towards the Sun. As this massive planet moved around, its strong gravity caused chaos and knocked asteroids loose, sending them hurling toward the other planets. The Earth and other terrestrial planets experienced a period of continuous bombardment from asteroids and other smaller bodies throughout the course of the following few million years. This period in solar history is typically called the Late Heavy Bombardment. Now, the beautiful Moon came to be formed millions of years later. This had a lot of scientists puzzled. Why was the Moon not created during the formation of the solar system? One such theory, called the Giant Impact Hypothesis, says that the Moon was formed when something crashed into the Earth. Earth originated from the residual dust and gas cloud surrounding the newborn Sun, just like the other planets. Many bodies were generated in the early solar system, which was a hostile environment, but they were never able to attain full planetary status. Not long after the infant planet's creation, one of them might have collided with the Earth. Theia, the Mars-sized object that struck Earth, melted pieces of the newborn planet's crust, sending them into space. The expelled particles were held together by gravity to form the largest moon in the solar system as compared to its parent planet. This type of formation would account for why the Moon is primarily composed of lighter elements, resulting in a lower density than Earth, which means the material that produced it originated from the crust, leaving the planet's rocky core unaffected. It would have been close to the ecliptic plane of Earth, which is where the Moon revolves at the moment, as the material gathered around what was left of Theia's core. Now, the Earth was not immediately habitable with flora and fauna everywhere. Rather, it was covered with molten rock and even radioactive material. The planet was agitated due to the constant bombardment and was full of active volcanoes. I guess we should be grateful it's no longer like that, huh? Imagine pools of molten lava everywhere. It's a scenario right out of hell. And while the temperature may be getting hotter these days, thank God it's no longer 4700 degrees Celsius. It only really became a planet where life could form and exist about 200 million years after it was formed. As Earth continued to cool off from the Moon's creation at this time, the bombardment kept it unsettled and volcanically active. Fortunately, at some point, asteroids and comets that contained ice and water collided with the Earth, releasing a large amount of water vapor. This vapor then went on to condense when the Earth cooled and began to fall on the planet as rain. For those of you who did not know yet, water existed only in its gaseous form until the Earth cooled down to around 100 degrees Celsius. The rain then went on to form our beautiful oceans. Despite the planet cooling down, supervolcanoes survived beneath the newly developed oceans as volcanic activity continued. And for nearly 700 million years, lava was still continuously flowing on the surface and life forms could not exist. Today, the volume of the Earth's atmosphere is roughly 1/5 of oxygen, which is essential for life as we understand it. However, it was not always like that. Although oxygen has been present in the form of compounds in the interior or the planet's atmosphere and in the oceans, oxygen as a gas did not start to build up in the atmosphere until much later in the planet's history. Our scientists have only just started to solve the puzzle of what the atmosphere was like before oxygen's emergence. Earth had to have had water in order to have an atmosphere, and an atmosphere implies that there was climate. So this brings us to the next question. What was the early Earth's atmosphere composed of? The Earth back then mostly consisted of nitrogen, carbon dioxide, and methane gases. Meanwhile, oxygen was seldom present in the early atmosphere. It was likely created when solar radiation split water molecules into air with hydrogen and oxygen. The lightweight gas hydrogen would have risen up above the atmosphere and gradually disappeared into space. The heavier oxygen gas would have swiftly reacted with minerals on the surface of the Earth or with other atmospheric gases like methane, drawing it out of the atmosphere and back into the crust and mantle. If something else was also making oxygen, it could only start to build up in the atmosphere if it was being generated faster than it was being eliminated, which would indicate that there may have been life on the planet. Who saw that coming? Thankfully, by examining the rocks on our planet, we were able to determine all of these complex information with a high degree of accuracy. Rocks preserve records of all the changes that they have gone through. They preserve traces of life and planetary activity within and keep a record of their own genesis and growth over millions of years. According to some studies conducted by geologists and scientists, methane-producing bacteria may have lived on Earth as long as 3.8 billion years ago, despite the spare fossil evidence we have. By 2.7 billion years ago, cyanobacteria, which are photosynthetic bacteria, had evolved. They had the power to use the sun's energy to transform carbon dioxide and water into food while producing oxygen gas as waste. They were shielded from the sun's harmful rays by the shallow waters where they inhabited, as the ozone layer was not present at that point in history. By 2.4 billion years ago, these organisms were so numerous that the free oxygen they produced started to build up in the atmosphere. The result was significant. The oxygen in the upper atmosphere created a protective layer of ozone that blocked harmful UV radiation from the sun and made the surface of the Earth habitable. However, because the Earth's magnetic field had started to form, the atmosphere could still be sustained. This prevented the solar wind from removing or destroying the atmosphere. The availability of oxygen, or O2, which is breathable and closer to the surface, allowed for the evolution of whole new types of life. One of the most remarkable aspects of life on Earth is how the earliest organisms produced oxygen, which helped later, more complicated forms of life to flourish. Here's a little fun fact. Did you know that zircons, which are gemstones from this era with very particular carbon ratios, may contain biological activity and water traces? It's widely believed and recognized that the existence of vast seas was one of the primary factors in the origin of life. Since liquid water is a universal solvent, it can carry every type of nutrient to any spot on Earth, allowing even the most remote regions to support life. The mere presence of liquid water on a body today is a huge draw for space travel because of its peculiar magical characteristics. To put it simply, life on planet Earth did not begin with humans, animals, or plants. Rather, the existence of bacteria led to the formation of what we now know as life, but we still had a long way to go. The Earth in its molten state began cooling down, and oceans started forming despite the volcanic conditions. From time to time, the surface would cool down and form land masses, but only to sink into lava once again. Then, after about 100 million years after its formation, Earth began to form a crust, and life on Earth was no longer a fantasy. The journey of Earth is so interesting. It's crazy to know the kind of drastic changes our planet had to go through to be what it is today. Talking of which, the Earth is still evolving into something else with each passing day. Billions and billions of years later, will the Earth remain as it is today? We'll let you ponder on that thought for a while. Meanwhile, back in the day, the birth of numerous tiny land masses took place in another 500,000 years. These later evolved into the focal point around which the modern continents formed. These rocks, which are now found in Australia, date back 4.4 billion years and are some of the oldest ones that have been found on the Earth. Talking of life, the earliest single-celled living forms could only be found in water. These could easily take in nutrients from their environment and process them for food in their bodies. Life became reliant on nutrients from rocks and water thanks to this extremely prehistoric mechanism. During the second half of the early geological ages, early unicellular bacteria started emitting oxygen and absorbing infrared light instead of visible light. This was simply an early form of photosynthesis. For the first time in history, photosynthesis allowed organisms to create food by themselves. This was a major change in the game, and life's rate of expansion was accelerated. Organisms went from single-celled to multicellular. As photosynthesis increased, the Earth's atmosphere underwent a significant alteration. It began as a disgusting mixture of carbon monoxide, methane, ammonia and nitrogen, and evolves into a far more toxic substance with a lot of pure oxygen, which was detrimental to all existing life. Even in the modern era, pure oxygen is hazardous to all life, including us, humans. Being aquatic, cyanobacteria also fill the oceans with oxygen. This led to the Great Oxygenation Event, which took place 2.3 billion years ago. The first extinction event and the first ice age were two significant occurrences on Earth, caused by the increase in amounts of this new gas in the biosphere. A large number of species were extinct within a short period of time in history. The development of glaciers was another consequence of the oxygen crisis. Many greenhouse gases, most particularly methane, were naturally eliminated from the atmosphere as oxygen levels rose. Wooded places are substantially cooler than cities nowadays because oxygen decreases heat. The power of the atmosphere to keep the planet warm was lost when oxygen saturation caused the average temperature to drop to 5 degrees Celsius, below that of today. A sudden sharp drop in temperature signaled the beginning of the Ice Age. The interesting fact about the Ice Age is that the temperature does not always stay cold. There are periods called glacial and interglacial. Glacial periods can last up to tens of thousands of years and more, where the Earth is covered in ice and temperatures are substantially colder. Interglacial periods, on the other hand, last only a few thousand years and are quite like the climate conditions we face currently, which means we, the residents of Earth, are currently in an interglacial period. Researchers are still trying to determine the origin of ice ages. The amount of sunlight that Earth receives from the sun is a significant impact. Due to variables such as the tilt of the axis, the amount of sunlight that reaches Earth can fluctuate quite a bit. The amount of sunlight that reaches Earth changes significantly over thousands of years, especially in the northern latitudes, the region near and around the North Pole. An ice age begins when temperatures drop and more water freezes into ice as a result of less sunlight reaching the northern latitudes. The ice age ends as temperatures rise, ice sheets melt, and more sunlight reaches the northern latitudes. But there are a lot of additional elements. Now let's talk about the land masses. Two supercontinents known as Valbara and Ur originated within a billion years of one another around 3.5 billion years ago. These continents were rather small, however, they are known as supercontinents since they were the only land masses in the area. Following that, other supercontinents known as Kenneland, Rodinia, Pangaea and Gondwana were formed as well. Pangaea was one of the first supercontinents that occupied about 1/3 of the surface of the Earth millions of years ago. A vast geographical mass made up of several continents is known as a supercontinent, although some were not even large. Nearly all of the Earth's continents were joined together to form Pangaea, to form a single landform. The general consensus is that Pangaea began to form more than 300 million years ago, reached complete formation 270 million years ago, and split 200 million years ago. Pangaea is derived from a word that was used in classical Greek and meant all lands. When Alfred Wegener observed that the Earth's continents appeared to fit together like puzzle pieces, he coined the phrase. At a symposium on the subject in 1927, he coined the term Pangaea and later established the theory of continental drift to explain the shapes and locations of continents. Yes, the continental drift is a real thing, and it's not just a part of a Disney's Ice Age movie series. Over time, this hypothesis developed into the contemporary study of plate tectonics. The present-day continent of North America was connected to Africa, South America, and Europe between 300 and 200 million years ago, and they all coexisted as Pangaea. When a three-pronged fracture developed between Africa, South America, and North America, Pangaea first started to split apart. A volcanic rift zone was formed when magma teared up through the crustal weakness and rifting started. As these split, continent-sized pieces of Pangaea diverged, volcanic eruptions threw ash and volcanic debris across the landscape. A new ocean basin, the Atlantic, was created as a result of the gash between the expanding continents. The supercontinents drifted apart due to the movement of the tectonic plates, which are a part of the Earth's outer shell, thus forming continents and countries as we know it. Many shifts later, we now have 7 massive continents. This is when life began to flourish. Plants and animals were present, although on a much smaller scale, and due to evolution, the world was taken over by mammals and their ability to reproduce. Reproduction and survival of the fittest created a land none of us could have ever imagined. As the climate was ever-changing, the species picked up traits of adaptability, and somehow, humans came out on top. And before we know it, we're in the 21st century, with the world at our fingertips and more advancements than we can even count. It all started out of nothing, and after billions of years have passed, the planet Earth is more developed than it has ever been. Could you ever imagine going back to that? Hot lava and barren land with no vegetation? Sounds impossible. That is all we have for you guys today. If you enjoyed today's video, don't forget to like, share and subscribe. To never miss out on a new video, click on the bell icon and stay